Hello everyone, my name is Darren Carmichael, and today I'm going to be using some data that I got from exoplanets.org and this interactive plotting program called GLUE to explore the question, is there some combination of stellar mass and stellar color that affects the number of exoplanets we detect orbiting any particular star? So first let me explain what I have in front of me here. On the left side is a scattered plot of stellar temperature versus stellar mass. The x-axis is in units of solar mass, and the y-axis is in units of Kelvin. Now, I'm using temperature as a proxy for color because stars are actually quite good approximations for black bodies. So in other words, that's saying the colder the star is, so down here, the redder it tends to be, and the hotter the star is, so up in this region, the hotter it tends to be. So on the right now, we have two histograms. The one at the top is describing the number of stars with what number of planets that we've confirmed orbiting them. So just reading it off, there are about 150 or so stars with two confirmed exoplanets in orbit around them. Or another way to see it is there are many more, around 580 stars with only one confirmed exoplanet orbiting it. So that leaves us with the last histogram here. So this is a distribution of those planets around their stellar mass. So again, the x-axis here is in terms of solar masses, and we see a peak again around maybe 1 to 1.1 solar masses. So that's saying most of the exoplanets we find tend to peak in their distribution around solar mass type stars. Okay, so now to explore this question, one thing I found interesting here while using GLUE is if we define a multi-planet system as having two or more planets, and then highlight that here, we'll notice in these other plots the results. So on the left here, we don't get, it's not very informative in terms of, we see, yes, there's generally a wide range of multi-planet systems around different combinations of mass and color. However, what we do get from this is that there does seem to be a trend that's followed from this low mass to low temperature or redder star range, all the way up to we get to higher masses and hotter temperatures or bluer colors, that the stars seem to cluster around this. Maybe if you want to draw an imaginary line here. I think what I found even more insightful was down here on this histogram. So if we take a look here at the distribution of multi-planet systems around stellar mass, we get a peak just around 1 more or less, maybe 1 to 1.1 again. However, if we just take single planetary systems and now look at that, we get this peak shifts up to 1.1, and that's much more clear than it was before with just multi-planet systems. And another thing I also found interesting is that if you look at this carefully now, we have our peak around 1 solar mass and kind of a more planets down between zero point 0.5 and 1 solar masses here than we have above 1. Okay, so now looking at the single planetary system population again, we get this. So our peak goes to 1.1, and instead of having more of the planets being down here, more of the stars and planets being down here, they seem to be focused more on the higher mass end of stars. So that's saying that, if we move this over here really fast, um, higher mass stars seem to be slightly more likely to form only one planet versus lower mass stars, because we now have a lower mass distribution here, being able to form more than one planet. So again, thinking of the peak, if we have a peak around 1 solar mass in a multi-planet, and these tend to have multiple planets, that is that allows the solar system to fit in that context, meaning that we have 8 planets here around the sun. The sun is 1 solar mass, so it would actually fit quite nicely into this distribution. In other words, it wouldn't be an outlier. So that's nice for putting that in context. And then conversely, which also again fits, if we just take stars with 1 solar mass, though those tend to peak in distribution around maybe 1.1, 1.2 solar mass stars, and they can get all the way out to these very, very massive stars around 3 solar masses or so. So that's just saying that from what we have in this data so far, uh, at the very least, we can sort of get a sense that higher mass stars tend to only want to have one planet form around them, while lower mass stars tend to have more than one planet. And this is a very fine distinction considering that our high mass stars peak around 1.1 to 1.2, and our low mass stars peak around 1 here. So with that, the last thing we can explore is the temperature distribution. So if I change this histogram down here from stellar mass to stellar temperature, we get this. Now, there are two peaks here, one around 5,000 Kelvin and another around maybe the sun's temperature 5,800 Kelvin or so. So we move that over here and do the same thing we just did. Uh, all of our multi-planet systems, that is with two or more planets, they, you might kind of roughly say, have this very wide distribution around the center of maybe 5,500 Kelvin. Again, that sort of fits the description of the solar system, and maybe you can convince yourself that, yes, that fits into that context. When we do just single planet systems, we get this. Um, it's a much broader distribution than in terms of stellar mass, but again, we do kind of see that there are two kind of populations that might want to form just around 5,000 Kelvin stars, and one on the higher end of temperatures here. So it's slightly less clear, I think, with color, but with mass, at the very least, we can kind of start to get the sense of that this particular type of masses around one solar mass tends to form more than one planet. Okay, so the last thing I wanted to say before I concluded was that all of this that we've just done here needs to be informed by our observational biases, and this is kind of something I learned when I was doing this whole experiment here. So an observational bias, an example of that would be, say, we detect a hot Jupiter around the star, and it falls into this column here. So that's one planet, one star. Well, a hot Jupiter is a massive thing, and it's more than likely that this planet may have washed out the signal of a smaller planet that may have also been in that system. In other words, uh, certain kinds of planets can mask the signals of their other planets are orbiting the same star. And so that would heavily influence, this histogram, and could also possibly change what we see in these other histograms of mass and temperature. So just going along with that, we always have to consider that we're not detecting every single planet that we see or that we might find around the star. We're only finding a fraction of them, and that will stay that way until we can improve our technology essentially. So I don't know, that's just something I picked up along the way, and I thought it's important to mention because what we see in front of us is not the whole story. There may be many more planets that would fill in this region or other regions of this diagram, but we just haven't detected them yet. And until we do, I think it remains very much an open question of what combination of stellar mass and stellar color affects the number of planets that will form around any star. And so with that, I'll leave you with that, and thank you for listening.